Hello and welcome to Lab 1B on Simple Part Modeling in Inventor. As a review, we've covered the role of sketching and solid modeling in engineering design, different classes of projection, and sketching tips and tricks. In this video, we're going to transition from sketching to solid modeling and look at an introduction to Autodesk Inventor. We are going to focus on simple part modeling steps of sketching 2D profiles and using some 3D tools in Inventor, the Create tools Extrude, Revolve, and Rib, and the Modify tools Fillet, Chamfer, and Hole. We'll finish off with 2 examples shown on this slide, as well as some troubleshooting tips to help you out with your assignment. So let's begin by going over the general scheme of parametric solid modeling, which is currently considered the most powerful computer-aided design or CAD tool. The first step in parametric solid modeling is the creation of a valid 2D profile. To be a valid profile, this must be a closed profile, like the L-shaped one at the bottom of the slide. The next step is to then move the profile along some defined path to create a solid, and here we move the L profile along a straight line normal to the profile, which is called an extrusion, and this generates a 3D base model. Once we have this model, we can add more features like holes, chamfers, fillets, and rounds to make an even more complex part. A great aspect of this modeling strategy is that we're able to go back and change dimensions of a feature without having to redo the entire model. Say we want to change a dimension of the chamfer here, that's no problem. We could easily do that without having to start from the beginning. At the end of the day, every parametric solid model is essentially a collection of features, which are characteristic elements or geometries of an object. When you approach solid modeling of an object, it's important to first break down the object into a set of these features that can be modeled one at a time. These can be features that add material to the part, like a rib, or features that remove material from a part, like holes. Both are features. And once we've determined the component features of an object, we then have to pick a base feature to start with. And to make our lives easy, the base feature should hopefully describe the overall shape or provide the most detail for the object being modeled. This way we won't have to add too many additional features afterwards. It's important to note that with parametric solid modeling, there really is no single right way to model a part. There are always multiple strategies that we can take to arrive at the same final part. So consider modeling a cylinder. Here are 3 possible ways that we could generate a cylinder using this parametric solid modeling framework. In option 1, we could start off by sketching a circle for our 2D profile, and we could simply extrude it upwards to generate a cylinder. Alternatively, for option 2, we could sketch a rectangle as our 2D profile, and we could revolve it around its edge. This would also give us a cylinder. And our third option could be to start with a 2D sketch of a square, to extrude it out to get a prism, and then we could round the edges of the prism to yet again obtain a cylinder. This last option probably isn't the best because it requires the most work, namely because our initial base profile of the square really isn't as descriptive as it could be. Here's a slightly more complicated part with an L-shaped profile, a rounded semicircular top, and a hole feature. And just like with a cylinder, there are certainly multiple ways for us to model this part. One option might be to start off by extruding the L-shaped profile, just like we saw before, then taking away material to generate the round feature and the hole. Another option could be to sketch the back profile of this part, which would be like a rectangle with a semicircular top, and we could even include the hole in the sketch. Then we could extrude that profile straight out, and all that would be left would be the removal of some material to generate the L-shaped side profile. The key idea here is that there's always different approaches to modeling a part, so keep that in mind as we work through the course. Now, parametric solid modeling has been implemented in a variety of CAD software, including SolidWorks, CATIA, Fusion 360, but for this course, we'll be using Autodesk Inventor, so let's dive right in. When you first launch Autodesk Inventor, the first thing that you'll want to do is create a new part, which is file type IPT. Different template part files exist for different measurement systems. To access these templates, make sure you navigate to File in the top left of the toolbar and select New to bring up a window to create a new file from Template. If you want to make a part in millimeters, select the metric folder and double-click on Standard Millimeter IPT file for creation. And if you want to work in inches, open up the standard inch file from the English folder instead. Once you create your new part file, the Inventor Part Model interface will pop up, which we will walk through briefly. To start, the vast majority of the window comprises the drawing area, with a menu bar at the top and a project browser to the left. As we generate sketches and features of our part in the drawing area using tools from the menu bar, those features will be documented in the project browser. To the right, we have our view cube and navigation bar, which will be useful in moving around the drawing area to see different views on our part. So initially by default, the menu bar is set to the 3D Model tab, and we'll look at a few useful panels in this tab. There's the Start 2D Sketch button at the far left, which we know will be the first step in solid modeling. And next to that, we have the 3D Create panel, containing tools that help us go from a 2D sketch to a 3D feature. Next to that, we have the 3D Modify panel containing more tools that, as the name suggests, allows us to modify 3D features. And if we go to the 3D Sketch tab, you'll see we end up with a similar tool ribbon that has a Create panel, allowing us to create elements of a sketch. We have a Modify panel and a Constrain panel, which we'll talk about in a second. So with this basic tour of the Inventor interface complete, we can now go through the general steps of part modeling. We've already covered step 1, which is creating a new part file. Step 2 is creating a sketch on some plane, followed by step 3 of constraining the sketch. Once that's complete, we can move to step 4 and use 3D modeling tools to transform our 2D sketch into a 3D feature, and after that it's just rinse and repeat with steps 2 to 4 until all of the part's component features have been modeled. Now we'll go into each of these steps in a little more detail, starting at step 2 of creating a new sketch. When you click the Start 2D Sketch to the left of the menu bar, the 3 XYZ sketching planes will appear in the drawing area for selection. You can pick any plane you'd like to start your sketch, but I'd advise you to select a plane based on what you plan to sketch so that the resulting front view of your part will match up with what you envision the front view to be. But don't worry about this too much for now. Once you select a plane, Inventor will switch to the Sketch tab in the menu bar. This leads us right into step 3 of making the sketch, as the Sketch tab provides a bunch of sketching tools for us to use, like the line, rectangle, and circle tools. We can use these to generate the basic shape of our profile sketch, but before we can take that sketch and sweep it out into a 3D feature, we first need to make sure that the sketch is properly constrained. Constraints are the geometric relationships, dimensions, or equations that control the size, shape, and orientation of elements like lines and curves in a 2D profile, and there are 2 types of constraints at our disposal in Inventor. The first is the dimension constraint, which allows us to specify the length of lines, curves, and relative distances between elements. And the second category is geometric constraints, which are applied to associate 2D geometric objects together or to specify a fixed location or angle. The remaining constraints listed here, coincident, collinear, concentric, parallel, perpendicular, tangent, horizontal, and vertical, are some of the types of geometric constraints in Inventor. These are applied by selecting the desired constraint tool indicated by the symbols in the constraint panel, and then selecting the sketch elements that you want the constraint applied to. Once these constraints are applied, only changes in geometry that do not violate the constraints are permitted. It's good practice to fully constrain your sketches, which you will be able to confirm in the bottom right of the Inventor window where it tells you the number of degrees of freedom remaining in your sketch. Or it says fully constrain once the degrees of freedom is 0. Doing so will prevent unexpected or accidental changes, and it will make it way easier to go back later and make changes to a part and obtain the desired outcome if needed. So how do we know how many constraints are required for a 2D sketch? Well, this is related to the degrees of freedom, as I mentioned before, which is the number of independent parameters that define the sketch's configuration. For example, a line segment has 4 degrees of freedom, which could be an XY position and its length and angle, or equivalently, its 2 XY endpoints. A circle has 3 degrees of freedom, its center point and its diameter, and both circular arcs and ellipses have 5. So after making a 2D sketch, we should always fully dimension and constrain it to remove these degrees of freedom. Once we have our fully dimensioned 2D profile, we have a number of 3D Create tools that we can use to bring our 2D sketch into 3 dimensions. The Extrude tool adds depth to a 2D profile, while the Revolve tool revolves a profile about some axis to obtain a 3D part. Note that both of these tools only work for closed profiles, so you have to keep that in mind when you are creating your sketch. Finally, the Rib tool will generate a rib or web support feature on a 3D part from an open or closed profile sketch. To create the sketch for the rib or for any other feature to be extruded or revolved, you might need to define a new sketching plane in Inventor, which can be done in the 3D Model tab with the Plane button. Some example options are creating a new work plane that is offset from some existing plane in your part model. This could be the surface of an object. And another option shown here is creating a plane that is angled about some edge. Once we have a base 3D part created, We can also use some modify tools like fillet, chamfer, and hole. The fillet tool allows us to round exterior edges and fillet interior edges. These both give the same general smoothing effect, where round removes material and fillet adds it. With the chamfer tool, we can bevel edges of a part, and the hole tool is no surprise. It allows us to make holes from defined points on a part. There are multiple types of holes, such as the counterbore hole, which is meant to accommodate socket head cap screws, and the countersink hole for flathead screws. The large diameter at the top of the hole means that the heads of the screws can be flush with the surface of the part. Additional hole types exist, and we will get practice with these as we continue through the course, but for now we will stick with your constant diameter hole. Now that we've gone over the basic steps for simple part modeling, it's time to try things out with an example. In an accompanying video, I will walk through how to model this part from a dimensioned isometric pictorial, and in a following video, I'll go through a second example of making a part from a dimensioned multi-view instead. These example videos will allow you to become more familiar with Inventor and with reading dimension part drawings. 2 more example drawings and part solutions are provided with the course content for your practice, and here are some tips when it comes to interpreting these drawings. To start, it is important to understand some common notation in these drawings, like R and phi, which indicate radius and diameter dimensions, as we can see in this example. Other common notation includes quantity indications, like this 2 times to indicate that this round feature appears 2 times on the drawing. And it is also important for you to look at all the views in order to understand the part and its dimensions. This is especially important as the part becomes more complex. For example, there are quite a few hidden lines in the top view that might look confusing in this example, so we need to consult the right view to understand that these correspond to this slot that goes all the way through the part. Of course, the more you practice, the better you will get at understanding these drawings, but in the event you feel like a dimension is missing, you should always look for other clues other than numeric values that will tell you about the part's geometry. This includes center marks and center lines. For example, we see only one center mark here, which tells us that this hole and round feature are concentric, meaning that the center positions are aligned or coincident. This center line also indicates that this part is symmetric, which will help in recreating the part. Also, don't forget about geometric constraints in addition to numeric constraints. For instance, in this cabinet handle example, we can assume that these 2 curves are tangent to help us properly constrain our sketch when modeling the part. When it comes to the center marks on this top view, we can see that the round base end circles are concentric with the handle mounts since they share the same center mark, and this other center mark corresponds to the rounded ends of the handle, which we can also verify from the front view as well. So these are some tips to keep in mind when you're reading drawings for part modeling. Here are some additional troubleshooting tips related to part modeling in Inventor that are also provided in a PDF document in the course material that you can consult on your own time to help work through any problems that arise while using Inventor. So with that, we've covered an introduction to simple part modeling in Inventor with 2 main examples, and this provides you with all the information you need to complete the Lab 1 assignment. Happy CADing!